Hello everyone, it has almost been 4 minutes. We'll start now. For those who joined late, my name is Ashutosh and I am the TA for Fiber Optic Communication Technology offered by Professor Deepa Venkitesh on the NPTEL platform. This is the first live interactive session, and the way we would like to do is I would go over the topics that have been go over the overview of the topics that have been discussed here, and then we'll delve into the assignments and solve some of them. You can interrupt me anytime in between if you have any questions or there's something specific you want me to address, and we'll get going. Is that all right with everybody? You don't have to say, you can just type and I'll try to answer those. So before we start, the interactive sessions are on every Friday, 6 to 8 p.m. in the evening, and we'll get started. So I believe all of you have gone through the lectures of the first session, week 1, in which Professor Deepa, in the beginning it was just setting the base as to how this course is going to go. There was a brief history of communication. She went over how currently it is primarily mobile driven, where you have 4G, even now 5G, but the backbone, the infrastructure, the entire infrastructure is supported by a fiber based network. The fiber is between your home to the nearest access point, from the next access point to the metro area. So if I draw it something like, although let us say this is the cell phone, and that is talking to a tower there, but all of this, after this for last mile connectivity, is connected by optical fiber. The reason for use of optical fiber is because it has low loss as compared to other methods. It is cheap and it has very high bandwidth. The other topics that the basic topics that were discussed by Professor Deepa was just setting the stage with what is a bit rate, what is a baud rate, and then the entire idea of conversion from analog to digital format. Because in real world everything is analog. Everything, by analog what we mean is everything is continuous. There are no discrete steps there. Whereas the processing that we do is discrete. Your mobile phones, your computers, your tablets, your laptops, everything uses bits. So your actual signal that is available in the nature is always continuous. It's just some time varying signal, S of t. Whereas the processing that we do on our hardware, on most of the hardware at least, the processing is done on bits, where you have ideally 2 levels. You have a logic level 0 and then you have a logic level 1, and your data bits are flowing between these two. Now this is just for representation purposes to show that we have an analog signal, and we have an analog signal which has to be sampled into digital, which is processed later. On our computers. Now after that conversion, what she talked about was called, this was just for setting the stage as to what is digital communication, what is fiber optic communication, and after that she went on to set the stage for modulation. Modulation is how we impose our information on the light carrier. We'll see more of that. And then she talked about different kinds of modulation that there is amplitude modulation, such as OOK, or called on-off keying. There is PAM4. PAM is pulse amplitude modulation. And 4 signifies the number of bits. We'll talk more about it. Then there is phase modulation techniques, then there frequency modulation. Now after setting the stage for all this, what she talks about is called spectral efficiency. Now we want to push as much data as we want. We want better communication speed. We want our Netflix to stream faster. We want YouTube to stream faster. And we have only a limited space in the optical spectrum. So how can we pack more data into it? Before we even answer that question, we have to first understand how to quantify what is the density of data that is being shipped in the bandwidth, and spectral efficiency is used to characterize that. Now let's talk a little bit about analog to digital. So like I had mentioned earlier, all the signals that you have in nature are predominantly analog. Now there are two ways to do this. This is an analog signal. Now there is this thing called Nyquist theorem. Nyquist theorem states that if I have to faithfully recreate the signal, I must sample it at twice the bandwidth. Now with just this statement, there are new terms that have popped up. It's like to faithfully recreate. That's one term. I must sample it. What does sampling mean? And then there's bandwidth that has come into the conversation here. So now we have, I am assuming that everybody here has a basic understanding of time domain and frequency domain. We are not going to go into the conversions, but we will see that every signal that is in the time domain, let's say a signal x of t that is in the time domain, if I take its Fourier transform, it will have a spectrum in the frequency domain as well. Some examples of these things are, if there is a sine wave, sorry for my terrible drawing, but if there is a sine wave oscillating with frequency omega, this is the time domain. The corresponding thing in the frequency domain, now frequency domain is written with positive and negative frequencies both, so this is your 0, and if the oscillation is a single oscillation of frequency omega, what you will have is just a delta function at point omega and another delta function at point minus omega, and this is your x omega amplitude, and this is just frequency. This axis is frequency. Now every signal in the time domain has a corresponding frequency spectrum. Now this is just a sine wave, and sine wave is a continuous, the figure that I have drawn on the right side, this figure, this assumes that this sine wave that is drawn on the left is continuous, it is never ending. So you have a signal sine omega t that is going from minus infinity to infinity. Now what happens is, when you have a signal like this, although it is interesting that you have a corresponding frequency conversion, we are not transmitting any information with it. By that what I mean is, our information is in bits. By that what I mean is, it's in ones and zeros. Now how do we get this ones and zeros? Let's say I have something that is going, that's an arbitrary state like this. Now the units of interest for us would be, let me change the pen color. I would be, so One thing to note, the difference between the Nyquist theorem and here is that Nyquist was planning to faithfully recreate the same signal, where here I am only interested in the data logics. I'm only interested in the digital waveform here. So what I do here is, this is your time and this is your amplitude. So the blue lines represent the time axis where I'm sampling it, and let's say this orange. Can I do this? I can do this. And the orange represents my quantization level. By quantization level, I'm just assigning different amplitudes to it. So let's say this is amplitude A1, this is amplitude A2, this is amplitude A3, this is amplitude A4. Now what I'm essentially doing after all this is that I am just picking up these data points. Okay. At same time, I'm seeing if it is above or below or anything. This is how analog signals are recreated, and my sampling frequency, or the time of sampling, if my time of sampling is Ts, then my sampling frequency F is 1 by Ts. Now correspondingly in the time domain, this will have some frequency spectrum. This is F cutoff. So Nyquist theorem states that I have to sample it at least twice the frequency of this, twice the carrier frequency, twice the bandpass limited. So my sampling frequency dividing Ts should at least be 2 of this. Can you record the session? Yes, the session is getting recorded. Small doubt. I'm currently over again. Just hold on, small doubt, sir. I'm just reading out a question and let me answer that. I'm currently in BTech second year, started last week. Would I gain most outcome if I study the course now without any prerequisite, or should I take the course in my third year? Please help me in this regard, sir. Monster. The person asking this question is saying that he is in BTech second year and if this course would help him. I am sure this course would be helpful, but in case of having the prerequisite knowledge, would depend how strong your mathematical foundation and engineering skills are, because although we are discussing Nyquist theorem, the course is fairly elementary. It just assumes a basic understanding in electromagnetism and some understanding of what the light does in frequency and time domain. You can continue with the course and take a short brush up, like a YouTube video or something, to understand what these basic concepts are, and after that you will be good. So I'll continue. Whereas in digital scheme, what we want is that our data is always between two levels, 0 level and 1 level. So let's say I'm sending 1 0 0 1. So the data I'm sending is 1 0 0 1, and for this I only have to sample it at each interval. I can sample it here, 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 such that on the receiver side I would get 1 point here, 1 point here, 1 point here, 1 point here, and 1 point here, and recreate my data. And after this I just put a normal thresholding. Whatever is above this is my logic 1, whatever is below this is my logic 0. So you see that transmitting data in digital is fairly simple. We are very easily able to collect the data which are bit 1s and bit 0s just by this. This was one thing. So few things to note here is that what is the quantization level? Quantization level just means how many discrete steps in y-axis. So there are two discrete levels, or how many discrete levels? What are the two discrete levels? One is level 0 and the other is level 1. So this is called quantization level. The second is bandwidth of the signal. Now bandwidth of the signal is similar to what we discussed earlier, where you have a frequency spectrum, and your data is encoded on this. Now this was just the basic foundation for that is necessary to delve into what we are going to discuss now. Now you understand that all the speaking that we do, or all the data that we have, it is in few kilohertz range. Like we speak between 2 kilohertz frequency to something like 4 kilohertz. Although our human ears are sensitive from 2 to 20 kilohertz, our speech is mostly localized in this region. Now if I have to take this data and transport it elsewhere, if I have to talk to somebody else, I have to somehow encode my information onto something that goes there. So it could be very simple, where I am the source or transmitter, that's me who wants to speak, and there is a receiver or listener that wants to know what I am sending. Now the way I send it across is called a channel. Now this is just a technical term, that is what is referred to connect the source. That is just a technical term that is connect the transmitter and a receiver is connected by a channel. Now this channel can be anything. The channel is anything that can transmit information. It can be the air that is surrounding in a room, or it can be a telephone line, or it could be this internet optical fiber connection that we are talking about. Now the reason we in the history of communication lecture, Professor Deepa talked about how there was gradual evolution of the kind of technologies that were used in the channel, and we found out that the optical channels have the largest bandwidth. By largest bandwidth, what we are able to do is, you can understand it this way, like there are 5 people. And there are 5 receivers. How do I draw the receivers? Now there are 5 people and 5 receivers. Now what is happening, let's say, is that this person wants to talk to this person, this person wants to talk to this person, this person wants to talk to this person, same as here and here. Now you have 5 people who are separated by some geographical distance. Let me use a different color. Now they are separated by some geographical distance. Now if everybody is speaking at the same time, yeah, Akash, please go ahead. Akash, if you have a question, you can type it up and I'll try to answer it, or you can speak. Go ahead. So if you have a distance where all the 5 speakers are trying to talk to the other 5 listeners at once, and everybody is speaking in the same 2 to 4 kilohertz frequency range, nobody will be able to make what is happening. nobody will be able to understand what the other person is saying because everything will get mixed up. This is what usually happens in a classroom, as my prof likes to say it. So the way to get around that is that we represent each speaker with the signal xt. Now, if a speaker is saying something, they have some information that they want to convey, that is on the xt. Now, what we do is called modulation. Modulation is very simple. Let's look at this first in the time domain and then in the frequency domain. Frequency domain. Now I have 5 signals. Let's, for simplicity, I'll just do 2. Let's say we have x1 and x2t. Okay. Now all of these guys are trying to talk to somebody else on the other side. Now what we will do is we modulate it with a carrier frequency cos omega t, and then the output becomes xc t cos omega t. Now this is because 1, let's call this cos 1 cos 2, and the user 2, the same thing happens with him. We take his signal, we modulate it, but we modulate it with a difference frequency omega 2t, and then we send it across xc t cos omega 2t. Now what this means in frequency domain is that, let's say my speaker was saying something and its frequency content was here. This is, I'm just assuming that the output is between 0 to 4 kilohertz, and this is minus 4 kilohertz. Now this is same for both the users in my case. 4 kilohertz minus 4 kilohertz. With modulation, what I have achieved, this is just a very broad level picture. So with modulation, what I have achieved is that I have moved this waveform, I have moved this frequency content to somewhere with frequency omega 1. So omega 1 frequency was here, and because of this operation, this modulation operation here, I have been able to move this here. Now because for my choice I had used different omega 1 and omega 2 here, that means these are at different places in the frequency domain. So if I say this is my omega 1, my omega 2 is somewhere here, and now this is my signal here. Now that you can see that both of these signals are in different areas of the frequency spectrum, and then they can be processed, they can be passed through the channel without interfering with each other, and on the other side the person will be able to receive it. This just goes to show that modulation has a benefit in which multiple information can be carried over in the channel without interference. Now just a small technical nomenclature clarity here. The original frequency, which is centered around 0, which was this, in our case it was 4 kilohertz. This is called baseband. Baseband signal. And when the same frequency got moved away from the origin, this is your origin, and moved to some frequency omega and it was here, this is called band pass signal. Okay. Now what is the benefit of doing this? I'll just illustrate that. The benefits of doing this is the same channel can be used by multiple people. Now this might be slightly tricky to think, but if you noise resilience, Now you see, light is actually oscillating very fast. Light has a frequency of about, let's say, 200 terahertz. So the frequency is in hundreds of terahertz. Whereas most sources of noise, most sources of perturbation are at much lower frequency. So what happens is, if this is your frequency spectrum and your noise is here, your signal is so far away that those kind of noises are less susceptible to damage the information content that is given on your carrier. So this is the benefit of, these are some of the benefit of the modulations. Now the next thing that we would like to do is look at the different modulation schemes. Now, from basic electromagnetic theory, we know that electric field is a vector, okay, which is represented by, in this case I am representing by Et. It is given by E naught e raised to the power j omega c t minus beta c plus phi. Now, physicists use I here and engineers use j. That is because for engineers current is also I, and we do not want to mix up our imaginary number and our current. So we will stick with the notation where j is an imaginary number. Now let us look at what are the different parameters in this which can be varied. Now if your electric field, which is a vector given here, is represented by E naught e raised to the power j omega t minus bz plus phi with a vector E, I have this thing which is amplitude, and e raised to the power j is the phase, is the entire phase of the signal, and this has the content where omega c is the frequency and this is the phase constant. Now you see, and this is the polarization. Now usually polarization is not used in modulation. So if I have an electric field E naught and I vary its amplitude, that means the rest of these terms remain the same, and I have my signal E naught 1 e raised to the power j omega c t minus bz plus phi and E naught 2 e raised to the power j omega c t minus bc plus phi. What this would mean is that whenever I am changing just the amplitude, that is called amplitude modulation. Similarly, you can guess that if I am changing omega c, which is the frequency, it is called phase modulation. It is called phase modulation. It is called frequency modulation. Apologies. And similarly, when we have phi that changes, it is called phase modulation. Now, these mathematical equations look complicated, but it is very simple to understand. What amplitude modulation just means that if I have electric field, if I have time, and if I have electric field here on this axis, I am just switching on and off the electric field. In actuality, it is not the electric field but square of the electric field that is switched on and off. That is just like switching on and off the light bulb. So if I have a light bulb, or if I have an LED, or if I have a laser, and I just keep turning it on and off, that is what will be called amplitude modulation. Now similarly, there are analogies to understand what the phase modulation looks like, in which the phase of the light, So light is oscillating very quickly. Light is oscillating at terahertz rate. So what that means is that even in a small time like this, there are multiple oscillations like this. Okay. Now in phase, what I would expect is that the light continues here. So let's say this is my 0 phase. Now what I expect here is that this will continue doing this, whereas in phase modulation I flip the phase, so it starts doing this. So you see, at this point a phase change occurred here. This is called phase change, and frequency change is just that the rate of this oscillation. So you have this is phase modulation, and then the third case is frequency, where you literally change the frequency of the oscillation. Now this is one, and at here you change the data and then you start using another frequency. Now one thing to note here is that whatever the encoding mechanism, whatever the encoding modulation scheme there is, there should be a corresponding detector as well. If I have something where I am varying the amplitude, like in the first case, or square of the amplitude, then I should be able to detect change in the square of the amplitude. If I have a case where I am changing the phase, like in this case, it should have been like this, but because of abrupt phase change, it started doing like this. So at this point, I should have something that should be able to detect the phase. Similarly, if there is frequency change, where you have two kind of frequency, this is frequency omega 1 and this is frequency omega 2, you should be able to detect changes in these kind of frequencies. So usually what happens till the last 10-15 years, amplitude modulation was the only thing that was being used, because detecting change in amplitude is very easy. To see if the light is on or off is very easy as compared to detecting phase of the light itself. So most of the deployments in the earlier were amplitude modulations. Then we realized that this is not enough, because our data capacity is increasing, we are getting data hungry, we want to watch YouTube, we want to stream Netflix, all of that together. So we had to increase our our capacity of information that is being carried over the channel, and then we started looking at some exotic kind of encoding schemes like PPSK, QPSK that ma'am talks about in her lectures. Now she talks about different kind of encoding schemes, whereas in amplitude we have OOK, which is on off keying, where you literally just turn the light on and off if you have a laser source here, and you can control when the laser is on or off, and you have some number that you want to send. Let's say you want to send 100,100. So what you will do is you will turn the laser on and then turn the laser off, and turn it off, turn it on again, off, 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 100,100. This is literally what is on-off keying, where you are literally turning on and off to convey if the presence and absence of your logical bits. So if I have a detector here, every time it sees the light, it says that, oh, I have registered 1. Every time it does not see the light, it will say I have registered 0. And in that way, it will be able to reconstruct the bit. What Deepa ma'am talks about is the representation of these different encoding schemes on the IQ plane. IQ plane is nothing but a Cartesian plane with two axes, where you have your real axis here and you have your imaginary axis, and all of these encodings can be like here, where OOK encoding, where a signal ST is E0, where there is light, and the second signal is nothing, where 0 plus 0 is a. So on this it would look like this is your logic 0 when there is nothing, and this is your logic 1. Now these logic designations can be arbitrary. You can have them flip. You can instead say that when the light is on, I would like to call it 0, but that would not really. It's just strictly a matter of convention. Hey Akash, do you have a question? Keep raising your hand and not ask anything. Please go ahead and type your questions if you have any, and I'll try to answer them. Now similarly, what she talks about, the second kind of scheme is BPSK, which is binary phase. Which is binary phase shift keying. So instead of varying the amplitude, in this case you vary the phase. So you vary, you remember electric field I had written as E naught e raised to j omega t minus kz plus phi, and there was this here, there was this here. Now in the first case, in the last case, in OK, I was varying this, whereas in this case right now I am varying this phi. So now ideally we would want to be able to have two orthogonal set of these numbers so I can actually detect them. The way it is usually done is you have 0 and pi phase, but it's not necessary. You can have pi by 2 and 3 pi by 2 as well in BPSK. So what it would look like on the IQ diagram is, again, you have a real axis, you have an imaginary axis, and let's say for pi your signals become e raised to the power j pi into e naught. Your 0 phase becomes e raised to the j0 e naught. You notice the amplitude in this case remains the same. So if I just put a normal photodiode out there, or something that sees the amplitude of the light, it will not register any change. I have to put something that can detect the phase in that case. Professor will talk about what are phase detectors later in the lecture, but this is what then it would look like. It would look like e raised to, this would be your 1 signal, and this would be your, let's call it 0 signal, and then this would be your pi phase shift. Now are two-level system the only case that we can do? What is restricting us from having more? What is restricting us from having, instead of 2, why can I not put 4 points on that IQ plane? Why can I not put 6 points on that IQ plane? Essentially, you are just being restricted by your electronics there, how fast you can do, and what is the detection rate. So one thing to quantify this thing is called bit rate and baud rate. Now in the last case, OK, I was transmitting on state and off state. So that number is represented by 1 bit. If it is on, I was saying it is bit 1. If it was off, I was calling it bit 0. So the bit rate, or the amount of information that is carried in 1 unit of time for OK, is 1 bit per second. 1 bit per unit time. Similarly, in BPSK, I had 0 phase and pi phase. Let's say 0 represented my logic 0 and pi represented my logic 1. Although these are phase encodings, it is still conveying only 1 bit of information. So this is also 1 bit per time. Now what happens is, like I said, we are only limited by how many levels or how many quantization levels we can have by our electronics. So there is nothing stopping us. Let's say this was my OK when light was here, and then light was not here, and then light was here again. So it was 1, 0, 1. So the amount of information I was conveying in bit, this was 1 bit, this was 0 bit, this was 1 bit, and there was this 1 level 1. But I might as well have 4 levels. By 4 levels, I can have 1, 2, 3. That would mean this would quantify 0, 0. This would be 0, 1, 1, 0, 1, 1. Now I can have my information do some kind of tapestry like now. In this case, should have drawn it better, but let us assume that this time t and this time t are same. Same unit time for each bit, just for the sake of me getting my argument through. But here what I am conveying is this is bit 0, 1, this is bit 1, 0, this is bit 0, 0, this is bit 1, 1. So here in 1 unit time, I am able to convey 2 bits of information, 2 bits per unit time. Although I am just transmitting one state, so I am transmitting one symbol. By one symbol, what I mean is that one intensity. I am just transmitting this, I am transmitting this, I am transmitting this energy level, I am transmitting this energy level. Although I am transmitting one signal signifies 2 bits. So when symbol per unit time is called baud rate, and bits per unit time, not one, and bits per unit time is called bit rate. Now you can see these 2 quantities are interlinked with each other, and if they are interlinked with each other, there has to be a relationship that connects the 2. So the relationship is bit rate, which is given by bits per second, and baud rate, which is given by baud per second. They are related by baud rate is equal to bit rate divided by log 2 of m, where m is the levels or quantization. Let us do a short example to understand this. For OK, how many levels were there? One is here 0 and the other is here 1, so there are 2 levels. M is equal to 2, and I am transmitting one symbol. So my bit rate, let's do baud rate first. How many symbols I am transmitting per unit time? I am transmitting one symbol per unit time. Now what is my bit rate? Bit rate is log 2 of m into baud rate, where log 2 of 2 into baud rate, where log 2 of 2 is 1. So in this case, bit rate is equal to baud rate. Let me write this. In this case, bit rate was equal to baud rate. That just means that these 2 quantities are equal here when there are only a 2-level system and per symbol. But if we look at the other case, by other case I meant when I had 4 amplitude levels. I had 0, 0, 0, 1, 1, 0, 1, 1. What is my baud rate? Baud rate was still one symbol per unit time. I can't do better than one symbol per unit time. But what is my bit rate? My bit rate in this case is log with base 2 m into baud rate. log with base 2, and this is 4 into 1. So this would become 2 because log 2 with base 4 is log 2 raised to power 2, so 2 comes out, and then you have log 2 with base 2, which is just 2. Just a side note here. And so here you can see that for PAM4, this kind of encoding scheme is called PAM4, where you have phase pulse amplitude modulation with 4 levels. This is pulse amplitude modulation, and 4 signifies the number of levels. So for pulse, for PAM4, baud rate times 2 is bit rate. Okay. Do we have any questions till now? Okay, go ahead. Before we get into assignment questions, let us look at what is called spectral efficiency. Now we have been talking about transmitting the data through the channel, and what happens, the entire quest has been to increase our data throughput. Now before we increase our data throughput, there has to be a way in which we can quantify how much data is being pushed. And we have to understand if there are ways for us to do it in a better manner. To quantify these parameters, we have what is called spectral efficiency. Spectral efficiency talks about spectral efficiency. Let me define it. Spectral efficiency, or SE, is defined as transmitted bit rate divided by bandwidth utilized. So if I have a laser, let's say I had some initial laser here at frequency omega carrier omega c. This is my laser frequency. I modulated it. By modulating, what happens? By modulating, the narrow line width of the laser broadens because I am taking my baseband signal. I had done something like, there is this baseband signal, and after modulation with frequency omega, you have shifted it to a different part. So my laser is my omega c, and what happens after modulation is, at omega c, there is a spectrum like this. The shape of the spectrum is just for illustration purposes. Now if my initial signal, that is my laser or carrier, and my initial signal centered around 0 had a bandwidth b, so it would be b. So this would be omega c plus b and omega c minus b. So my entire frequency got shifted, and the bandwidth that is utilized is 2b in this case, because this is omega c plus b minus omega c minus omega b, which would lead you with bandwidth would be 2b, which is the same as in this case. So the initial bandwidth was 2b, and that is the bandwidth that is being utilized here. Now transmitted bit rate would depend on my kind of encoding that we do, and I believe Professor Deepa also goes into a few examples to discuss what are these different ones. She also talks about what is called Nyquist frequency. Nyquist frequency is a special lambda by twice the sampling rate, which says that you will be able to more efficiently utilize it. Nyquist frequency is essentially the minimum frequency spectrum, minimum frequency in the spectrum domain that is required to transmit that information. And with that, I think I have briefly covered the lectures. I would still advise you to go back and watch all of them for a greater attention to details. And after this, if anybody has any questions, this would be the right time to take them. Okay then. If there are no questions, we will move on to discuss the assignment questions that are there. I believe all of you guys have access to the assignments. Could somebody tell me if you have access to the assignments? Okay, thanks. So let us look at the first assignment question. First assignment question asks, which of the following optical C-band. The question is fairly straightforward. It is asking what is the wavelength range that is in the optical frequency C-band. Now C here signifies the conventional band. And these are textbook numbers, and you should easily be able to find these numbers. Now the second question is, which of the frequency wavelength fall under the visible spectrum? Now, to answer this question, we have to know a few things. We have to know that the frequency, I remember the wavelength. So the wavelength of visible light is between 300 to 700 nanometers. This is just something that we know. We know that 532 nanometer is green light, which is favored for underwater communication. 405 nanometer is used in many quantum processes. .630 nanometers is red light. I see, Sunil. Thank you for that. So these are just the numbers that you remember because you have interacted with the same field for so long. You are not expected to remember these numbers, but as it turns out, because you have used them so frequently, you remember them. So question number 2, the answers that frequency of the wavelength. So the option 2, one option we have figured out from this is that the wavelength of 600 nanometer. This is my right answer, and you will notice that this question does not have radio button. This has tick marks. That means there are multiple answers for this which can be correct. So we have figured out the wavelength. Now let us also look at the frequency. Now the relationship between frequency and wavelength is frequency times wavelength is speed of light, or it is written as frequency is written as nu, wavelength is written as lambda is equal to c. Yes, Sunil, go ahead. Oh yeah, thank you for letting me know that. So let us look at the first option of 600 terahertz. Now give me a sec. Yeah. we are given the first option is 600 terahertz. Now terahertz is a unit. Tera means 10 raised to the power 12. Giga means 10 raised to the power 9. Mega means 10 raised to the power 6. So I am given nu is equal to 600 terahertz. I do not know what it is in terahertz. So because we have established that the wavelength 300 to 700 or 350 to 750 is the visible region. Let's see if the 600 terahertz fall into that range. So the way we will do it is, we know nu lambda is equal to c, where c is the speed of light. In free space, so lambda is equal to c by nu. I know c is 3 into 10 raised to the 8 meter per second, and this is 600 to 10 raised to the 12 hertz. This 200, and this comes out to be 500 into 10 raised to the 9 meter is 500 nanometer. So this is well within 500 nanometer is within our wavelength band of visible light that we had established earlier. This means that 600 terahertz also corresponds to a visible light frequency. Similarly, there are two more options that you can go ahead and check. Now the third is again a standard textbook question. Band used by Wi-Fi. This is a standard textbook frequency number that is there. The reason these questions are included in the first assignment is that you are not yet familiar with the technical aspects. So this forces you to go through the textbook, or these forces you to Google the numbers and see what is the right answer. Now the fourth question is, for a complex modulation system with a symbol rate of, so that I have been given some numbers, so let's write that down. I am given a symbol rate of 10 gigabaud, and I have given a modulation format which is 16 com. And the question is, what is the effective bit rate? Now the way to answer this question is to first, whenever you are attempting any numerical question, the first thing you should do is you should write all the information that is given to you, which I have done in this case here. You will see that this is the question number 4 in your assignment sheet. I have written all the information that was given to me, and now I try to relate with what formula I know that contains these quantities. So I have been given symbol rate, modulation format, and I have been asked what is the effective bit rate. Now 16 com using a 10 gigabaud. So 10, now QAM is quadrature amplitude modulation, and 16 is the quantization number. So I had written a formula earlier which said bit rate by log 2 m, this is m, is equal to baud rate. From this you can find that bit rate is baud rate times log of base 2 m, which in this case would be 10 gigabaud into log 2 of 16. 16 is 2 raised to the power 4, so this becomes 40 Gbps, and that is how that gives me the answer that the effective bit rate is 40 Gbps. Does anybody have any questions on this? No. Let us check the next question. The next question is in QPSK. Next question in QPSK, the effective bit rate is. Now, before we answer that question, we have to understand what QPSK modulation is. If you'll remember your lectures, QPSK modulation is just 4 bits, and you can have them by any convention. This could represent 0, 0, 0, 1, 1, 0, 1, 1. All of these numbers are arbitrary. This can be a phase of pi by 4, minus pi by 4, 3 pi by 4, minus 3 pi by 4. So, how many quantization level? 4. Therefore, my log 2 of 4 is equal to now after that, after you have this number, you can use the relation baud rate into log 2 of m is equal to bit rate and arrive at the solution. Now, the sixth question. Which one of the following has the highest spectral efficiency at Nyquist sampling rate? Highest spectral efficiency Now, the options that have been given to me are 16 QAM at 10 gigabaud, 16 QAM at 20 gigabaud, similarly at 30 gigabaud and 40 gigabaud. Now, we have seen that spectral efficiency is defined as transmitted bits divided by bandwidth utilized. So, and transmitted bit rate. Now, one thing that happens here is that when you write this fraction out by transmitted bit rate via utilized bandwidth, and all of these are 16 QAMs, mind you. So, what happens is when you go from 10 gigabaud to 20 gigabaud, from 20 to 30, 30 to 40, what is happening is your transmitted bit rate is increasing. It is doubling every other step. But as so it happens, because the modulation pattern is same, the modulation pattern in all of them are 16 QAMs. The bandwidth utilized is also increasing. Now, what that would mean is that the increase in bit rate is accompanied by increase in bandwidth. So because these whenever there is an increase in bit rate, because my modulation pattern is same, I am using more bandwidth. What that means is that their ratio is constant. Hence, the answer is all have same bit rate. Not bit rate, all have same spectral efficiency. This can easily be shown with the example that Professor Deepa had shown in the lecture, where you have a signal, let us consider 16 QAM at 10 gigabaud. My spectral efficiency is given by transmitted bit rate divided by bandwidth. Now at Nyquist, this is the bandwidth that I am utilizing. If this is omega c, this is omega c plus p by 2, omega c minus p by 2. Now we have already seen multiple times the conversion from bit rate and to baud rate. Bit rate is log to 16 into baud rate. So this just becomes 216 into baud rate, which is 10 gigabaud. And similarly, the bandwidth, the Nyquist bandwidth is this entire range. Now the way to find this is omega c plus p by 2. I am subtracting this minus omega c minus p by 2 is equal to this, and this cancels away, and this becomes p by 2 plus p by 2, which is equal to p, and b in this case is 10 gigabaud, not gigawatt, gigahertz. So you see that your efficiency is just 4 bits per hertz per second. That is your spectral efficiency, and it is same for all. This is same for all other cases because the modulation scheme has not changed. That means the more data you are pushing out of the same modulation scheme, you are broadening the spectrum as well. You can attempt the other cases and we can meet the next time if you have any questions. Now let's do question number 8. The number of photons in pulse duration of 1 nanosecond at 1550 nanometer if the power is 1 microwatt. Yes. Now I have been given the power, the wavelength and the pulse duration. Now I know that power is energy per unit time, and energy of a photon is given by h nu, or h c by lambda. I am utilizing the relation that c is equal to mu lambda. Okay, so if I substitute this back here, power into time is equal to n number of photons and energy of each photon. And then my power, it has been given to me that the power is 1 microwatt, time is 1 nanosecond into 1550 nanometer divided by hc is equal to n, or n is equal to micro is 10 raised to the power minus 6. While doing calculations, we prefer to have everything in the SI units. 1 nanosecond is 10 raised to the power minus 9. 1550 nanometer is 10 raised to the power minus 9. Now h is Planck's constant, and its value, if I remember correctly, is 6.626 into 10 raised to the power minus 34. You will have these numbers in your calculators. It's saved in the symbols there. And c is speed of light, which is 3 into 10 raised to the power 8 meters per second. So you put these numbers, 6.626 into 10 raised to the power minus 34, and you substitute for the speed of light. And I had gone ahead and I had done the simplification for all this, which turns out to be 7802 photons. So you would get some fractions there or some decimal points there, but photons cannot be split into two parts, so we just round it off to the nearest whole number, and from there we get 7802 photons in that pulse. Now let us look at the next question. The next question is, what is the modulation format you would pick if you had to transmit 100 Gbps but a symbol rate of 25 gigabaud? I am given a bit rate. Gbps. I am given a baud rate, which is 25 gigabaud. Now this comes down to the same relationship we have been playing with again and again, which is bit rate times log 2 of n. Oh, sorry, it's the other way around. Yeah, it's the other way around. Sorry, I had that mistake. Bit rate is just a second. Log 2 of m into baud rate. Now, just 1 second, please. Hey Gopal, hey, can you see Amazon package is there? I'm in a lecture. Can you see Vilashni's grease is there? Amazon, Vilashni's grease. Yeah, sorry about that. I have been given the baud rate in the question, I have been given the bit rate in the question, and from that you can calculate m, and this will give you your modulation format. Now let us look at the next question, which is with the power from a transmitter is 10 milliwatts. Power is 10 milliwatts. Distance is 100 kilometers with an attenuation rate of 0.2 dB per kilometer. Now, attenuation rate is the loss that is there in the fiber. Now, what happens is, if attenuation is given for 1 kilometer, which is 0.2 dB per kilometer, and I have to find it for the entire length. I will take alpha and multiply it by the total length. So it is 0.2 dB per kilometer into 100 kilometer, which means 20 dB. So the loss in the entire system is 20 dB. Now the first question is the power at the end of the fiber. Let's take that to the next sheet. Now, dB scale is a logarithmic scale. Logarithmic scales are helpful when the order of change is magnitudes apart. So that if I go from 1 to 10 to 100 to 1000 to 10,000, these numbers in a linear scale are growing arbitrarily large. But when I do it in log scale, this becomes more manageable. So the dB conversion for optical power is dBm is 10 log 10 power divided by 1 milliwatt. Similarly, loss, this is for power. Similarly, loss is minus 10 log 10 power. This is your loss, and loss comes with a negative sign because this signifies a reduction in the optical power. Now we know the power at the, we know the loss in the system. We have calculated loss in the system is, we have calculated attenuation in the system. Attenuation in the system is 20 dB, which means that the loss is minus 20 dB. Attenuation means the signal has been reduced by 20 dB. The other way of saying that is that this loss in the system is 20 dB, whereas the power of the transmitter is given 10 milliwatts. So if I go and put that in the my neat little formula up here, I can find it in dB scale. So power at output in dBm is given by 10 log 10 milliwatt by 1 milliwatt. This cancels and this is in dBm. Oh yeah, one thing to note here is that power is written in dBm. The unit for power is dBm when it is written with respect to milliwatts, whereas loss is always represented in dB or decibels. Okay. Now this simplifies to log 10 of 10, which is just 10 dB. Now we can see that the power output of the laser is 10 dB and the loss in the system is minus 20 dB. So power at the receiver another interesting fact about logarithmic scales is that factors like loss and gains just become linear addition and subtraction. So I had my p input plus loss. I am saying plus loss because I have accounted for the negative sign there. Negative sign already accounted. My p in is 10 dBm and my loss is minus 20 dBm. So this just becomes minus 10 dBm. So that answers your relevant question. And now if I have to convert this back into microwatts, which is question number 12. What is the value in microwatts? So we already had the expression where it was dBm is equal to log 10 P in by 1 milliwatt. We will reuse the same expression. We are given minus 10 dBm and this is milliwatts is 10 log 10 P in milliwatts divided by 1 milliwatt dBm. dBm goes away. This 10 becomes minus 1 is equal to log 10 P in milliwatts by 1 milliwatt. This just means P in is equal to 10 raised to the power minus 1 milliwatts. Now you can take this and you can convert it back into microwatts and you'll have your answer. I believe the last question is already addressed in the YouTube channel, so I'm going to skip that. Does anybody have any questions, any comments? Now I'll be taking them. Anything specific that you would want me to discuss, or anything that you feel I glossed over and you would want more information on, please feel free to speak out or drop a message in the box. If not, this is where today's live session ends. I'll be uploading this recorded live session on YouTube, and with the slides or my handwritten notes that are there, you should be receiving the assignments, and if there are any confusions there, please feel free to reach out to the NPTEL team. Thank you.